interesting things to do that. So a few words about viscosity solution and first order Hamilton-Jacobi equation. By the way, my set of lectures is supposed to be the preparation for the second week lecture series of lecture by Professor Bitake, just to go further in terms of studying the dynamics. So before going deeply into first order Hamilton-Jacobi equation, let me list some sort of sets of equations we can study by using viscosity solution. So the first order Hamilton-Jacobi equation, so the short HE equation. First order is often means this equation ut plus I'll explain h of x du equal to 0 in Rn cross 0 infinity, something like that. And we have some initial data. I'll explain the notions. Or sometimes I'll consider some other equation of the form lambda u plus h of x du equal to 0 in Rn with some lambda greater than 0 given or something like that. Greater than equal to 0 given. Here, u is u, x, and t that maps from, okay, in the first case, Rn times 0 to infinity that maps to R. So u is just scalar. Unlike the previous lecture, u is a vector field. Here's u is just a scalar function. And ut is just du over dt, so the time derivative. And in the context of this thing, we use du for the gradient in x. So du is basically gradient in x of u, or it's du over dx1, du over dxm. Okay, so that's the notion. So this is first order Hamilton-Jacobi equation. Now this is the classic second order Hamilton-Jacobi equation, or people call it Hamilton-Jacobi-Bellman equation, HGB equation. So something like ut plus h of x du d square of u equal to 0. Some more complicated equation. With d square of u is a Hessian. It's a Hessian of u. So it's a n by n matrix. And some more examples that I might go through is, for example, we can see the mean curvature flow. Something like ut equal to the gradient square diversion of du over du. I'm not explaining this, for example, now I'm just explaining this. Or we have infinity Laplacian. I might give you some just sort of interpretation of this. Ij, uxi, uxj, uxi, xj equal to 0. And then in this class of equation also there are some, I'm not going to go into this, but there's also the Monchapet equation, for example. I only get it wrong if you d squared u and stuff like that. But this is second order. It looks more fancy. I'm just going to do first order. But there is a kind of dictionary saying the following. So viscosity solution actually fits with equations that have maximum principle. So this is sort of a general kind of dictionary for us to use. So if you have equations that don't have maximum principle, there's no theory of that in terms of viscosity solution. Okay. So just sort of like, there are also a lot of other equations that related, but I just want to sketch some examples and stuff like that. Okay, so now let's go to first order or the Hamilton-Jacobi equation. Okay, for example, the equation of that simple form ut plus h of x du equal to 0. Okay, h here is basically h stands for Hamiltonian. And it's after the time that is the total energy. So it's kinetic energy plus potential energy. Okay. I will give you some interpretation later about why we have H is a Hamiltonian, why is it the total energy. But in general, basically we have the Hamiltonian and normally the total energy is conserved and so on and so forth. But to go it that way is too long. So I'm going to give you one derivation of Hamilton-Jacobi equation. So one derivation. We're going to do more derivation later. But this is a real way. By the way, my lectures is set in a not conventional way. It's kind of going back and forth, jumping, back and forth in terms of time. But I want to design in such a way that you feel more comfortable without, quoting a lot of things. So one derivation is coming from the very late observation 20 years ago, coming from the Lensset method. So this was first numerically. Surprisingly, numerically by Osler and Siltian. So this is a very famous result by Stanley Osler and Jeremy Siltian at Berkeley and UCLA. And then it was realized later on, theoretically, by Emmons and Spurr. And Chen Gigabuto. Of course, there are a lot more reference, but those are the first papers on this Lensset method. And I want to describe something. So how it goes. So for example, let's say you're given a surface. You're given a surface, let's say a very nice surface of n-1 dimension. You're given a surface in Rn of n-1 dimension, which is very nice. And now let's say you want to move this surface up. You put some rule, some law to that. For example, at each of the point you want to move it by some rules, whatever rules you like, something like that. You move the surface. And the question is that, so let's say at time t is the surface. At time t. And then the question is that how do we model such a thing? How do we model this problem? And for example, if you were to put here, the velocity is a mean curvature, you're going to have mean curvature flow. If you were to put some simpler velocity, you're going to get Hamilton-Jacobi equation. Okay. And of course, in differential geometry and stuff like that, there has been already a lot of studies in this thing, and they study it very deep work. But one way to kind of model this problem is kind of cute. Instead of looking at just the levels, just the surface, you're gonna embed the surface into the level set of some equation. So some function. So now you assume that you can put some function u0 here, where u0, let's say less than 0 here, u0 is greater than 0 here, and it's equal to 0 on gamma 0. Okay. So let's say you have gamma 0 is basically the values of x in Rn, so that you have u0 for x is equal to 0. So this is why it's called level set method, because for gamma 0, put it to be the 0 level set of this function. Less than 0 here, greater than 0 here, equal to 0. And then you assume, okay, heuristically you also assume further that also there exists a function. I don't know why I have such an existence, but why not? Let's just assume that there exists a function u depend on x and t. By the way, this is not French style. French style is to put time first. I want to use it first. So x first, count later. I think this is American. I don't know, but anyway. So assume that I have a function with x and t that can really capture the level set. So the x is a function of that whatever from Rn times 0 infinity to R that I do have gamma t. The surface in gamma t is being captured as the 0 level set of this function. Okay? You assume that you can capture like that. And now you're gonna try to model the movement of the surface by this function. Okay? Then now how to model the behavior of gamma t. Okay, let me give you two examples. So first example is that now let's say I assume that at any point of the movement I have it moves in terms of the normal direction with some velocity ax times the normal vector. So assume that the velocity, the normal velocity and at any point x on gamma t is the velocity is basically equals to ax times the normal vector. So that I have this movement at any point on the surface. I have a velocity. I can change that in the end, but I have this. So now, if I were to keep track with one particle, like David lecture, like let's say I start with this particle and I want to keep track of them, it's just satisfy very simple ODE. So the ODE for that is I have x of 0 is equal to y and I have x dot